So this question is asking, draw resonance structures for this. And I think this is a nice question because it really helps us understand and back up and understand, right, something about, well, this is obviously an aromatic compound, something about hybridization in resonance and in a ring. And right, there's two lone pairs in this oxygen, and what hybrid orbital are those lone pairs actually in? So, first thing, let's number some carbons, or atoms even in general. 1, 2, 3, 4, 5, 6. These are all part of the p orbital system, right? They all have a p orbital. All these are lined up. Carbocations are sp2 hybridized. We'll talk more about that. So p orbital's there. Easy move to make will be just to break the bond between the pi bond between 2 and 3. Have those electrons go to make a new pi bond between 1 and 2. So now where is there a plus charge? Which atom?
On carbon 3.
Carbon 3, perfect. All right, we want to balance our charge. Good. What's another resonance structure we could draw? Well, this is actually a really good, really stable resonance structure because the next move we make is actually going to make things have a full octet. Remember, what's the most important rule? The octet rule, right? If you follow the octet, that's going to be the best resonance structure. Who cares if oxygen has a plus charge? It's okay. It's all about the octet rule. Those two electrons can go there. Plus charge on our oxygen. Number our atoms. 1, 2, 3, 4, 5, 6. When I'm doing this numbering, it has nothing to do with naming. It's just me deciding number one's here. The key, though, is if you're going to do numbering, right, that you're consistent across, right? Make sure your numbering system follows from one structure to the other. All right, so let's label these A, B, and C. So the question is, which one of these is the most stable or the best resonance structure, the major contributor? It's C. Why C? Octet rule. C, all these atoms have full octets. Yes, there's a plus charge in the oxygen. Those dot structures can lie to you sometimes. It's okay. Octet rule. This is the most stable. So C is the most stable. What's the least stable? Which one is the least stable? Indeed, B is the least stable. Why is B the least stable? So C, everything has a full octet. That's great. B, you have that allylic, which I'll talk more about. That's allylic carbocation. How many hydrogens are on this carbon? How many carbons is this bonded to? It's bonded to 2, has 1 hydrogen. This is a secondary allylic carbocation. This is a tertiary allylic carbocation. Tertiary allylic carbocations are more stable than secondary. And that's because of hyperconjugation. And we'll back up and talk about that when we review carbocation stability. Okay, so we're looking at maybe a different way to do this problem. There's nothing, this is all good. This is all good. I just did it in one, instead of doing it in 2 steps and showing 2 resonance structures, I did it all in 1. Fine. So this is all good. But what happens sometimes, I think people get stuck and they're like, well, wait a second, I need to make another resonance structure here somehow. So one thing that people might do is this. And so this is wrong. Don't do this, but I'm going to show it to you. Why is this wrong? What's the problem? I balance my charge, I guess. But what's the problem? Is this lone pair? Is this lone pair part of the p orbital system? Right? Go back and look. No. It's in an sp2 orbital. It can't do resonance. Right? It can't do resonance. So don't forget those basic things. The other thing people might try to do is even push another pi bond this way. But again, this oxygen has no more places to go. It already has a full octet. You can't give it more electrons at this point. Right? So two things. Be careful about this is that synthesizing that, those hybrid orbitals, right, that we talked about, a p and an sp2 where they're at. That matters to understand these resonance structures. But this is a common thing I see sometimes, that people are trying to do extra things. They just forget, oh wait, that lone pair can't do that. That lone pair is in an sp2 orbital, not a p orbital. It can't do resonance. So we're looking at diene, di meaning two, ene, right? Alkenes, diene. It's actually an important type of molecule for the Diels-Alder reaction. It's one of the important reactions that makes all the steroids in our bodies. It's actually a really powerful reaction. The advanced organic students are doing this in the lab right now, actually, this reaction. So they're asking for resonance structures. So it's a conjugated system, right? So it's conjugated. What's the simplest resonance structure you could draw? You could simply draw the electrons going there. To give
Dr. Wenzel,
yes.
I don't know if it's just me.
All right. So it did the resonance, had the electrons go from the pi bond between 2 and 1 just to 1. Now, why did I do that? Why did I put the electrons to 1? What kind of what did I just? What I made a carbocation here, right?
Tertiary.
Say what?
Tertiary carbocation.
Secondary carbocation.
Oh yes.
But it's allylic. Right? It can be stabilized by a resonance form right here, right? So that makes it more stable, right? Because it can do resonance. Resonance always stabilizes things, right? Things that are conjugated are going to be more stable. And aromaticity is like the most special type of way to be stable. So we put the plus charge here, right? Move the electrons this way, so you have a plus charge here. Versus, right, allylic is better than tertiary because allylic can do resonance. So this is one resonance form, and then of course the other resonance form would just be this one. All right, so those are the two forms. And then they ask you which one's more stable, most likely. So the more stable one is going to be the one that has the charges, the opposite charges closer together. This is the more stable one, right? Because opposites attract. So this will be the more stable one. So this is one of our quiz questions. So this nitrogen is sp hybridized, and it's tough to see why that is. It's because this lone pair can do resonance with this sp hybridized carbon. And this is what I knew was going to be a really tough question. This is what I knew was probably going to be the toughest question on the quiz. And I thought of that. I knew that was going to happen. You really need to think about what the orbitals look like here. So because this carbon is sp hybridized, right, it has two p orbitals that are both, right, 90 degrees away from each other, right? This nitrogen has a pi bond with that carbon, right? That lone pair, though, is actually over here in another p orbital. And you notice how it's lined up with this pi bond between the carbon and silicon. Because then it can do resonance. What does that resonance look like? Because see, if I move these two electrons to form a pi bond here, that necessarily breaks this pi bond. Right? The two electrons in that pi bond. and those electrons will go to the silicon. So that's why it's sp hybridized.